Okay, hi everybody. So this is an AP question from the, I believe, 2018 free response part. And I thought it was really applicable to what we were doing and kind of a good way to review all of these magnetism ideas. So I just kind of want to go over each one and yeah, we'll go from there. So I just want to kind of talk through the ideas because this gets pretty complicated. This gets into like some pretty tricky stuff. So I just kind of want to talk through it and see where we go from there. So this first part is saying, okay, in a coherent paragraph length response, compare the magnitude and direction of the current at times t1, t2, and t3. Include an explanation of why there is or is not a current and the direction of the current if one is present. Use fundamental physics concepts and principles in your explanation. So what I want to start off with when I'm going over this is this idea of flux. So we said that flux is the symbol, and really what it stands for is the amount of magnetic field within some area of a loop of wire. And the main thing with flux is, yeah, sure, it exists, but the big idea is that if we change our flux, like if our flux changes through some amount of time, then we get this EMF, we get this voltage, we get this push of our electrons, so we get this voltage. And we also know that voltage, this is just another way of saying voltage, just saying it's coming from a different spot. This EMF, is equal to I times R based on Ohm's law. So we can really say that this EMF equals I times R. So my change in flux over time is equal to this EMF, this electromagnetic force, which is also equal to I times R. So that's really what I'm starting with. And then what I can also say is, instead of just writing flux over time, this change in flux over time, I have magnetic field times area equal to my flux over some amount of time. So I can just replace this with magnetic field times area to equal I times R. And now is where things get a little bit confusing. So hopefully we are on this track. And when we're thinking about this idea, we don't care about just the area of our loop. Like, sure, our loop has an area. Let me make a quick little loop. Our loop has an area, but we don't really care about the area of the loop. We care about the area of the loop that is within a magnetic field. So if this is my loop, I can kind of come over here. I'll make a quick copy of it. I don't know where it went. Oh, it's all the way down here. Cool. So this loop, it has some dimensions to it. So it has some sort of height that I'm going to call just some height y. Oh, that's too big. So it's going to have some height y. And then it has some length. I'm going to call it d. I'm going to make it some sort of defined length. So this hoop, the dimensions of it, in a total sense, the total dimensions of this hoop, the total area, is just y times d, the height times the base. That'll tell us the total area of this loop. But what we really care about when we're looking at this situation, we're going to care about the amount of... There we go. We care about the amount of area that's actually within our area. Or within our magnetic field. So I'm going to call this some distance x. So I'm going to call the distance and the x-axis some distance x. So if we're thinking about like the effective area, the area that's like inside the magnetic field, I'll call it a sub b. It's going to be x times y. Oops. And the thing about the area within the... Oh, I changed this to a, that's okay. The thing about the area within the magnetic field is that it is... The thing about the area within the magnetic field is that it is changing. It is not a constant value because we have this loop moving through at this constant velocity. So we have this area changing, and because we have a change in area, we have this change in flux. So because we have this change in flux, then we get this, that's changing, this quantity is changing over time. It means that we induce this EMF. So this area is changing, and next we have to figure out how much our area is changing by. So we have to think about this change in area. So we know that our a constant speed, a constant v. So because it's moving at a constant speed, we can say, oh, it's covering some sort of constant distance in some constant amount of time. Its velocity is constant. And then, let's say constant over here. Its velocity, this change in x over the change in time is constant. And then what we can look at is go, oh wait, x, we use x, we defined x to be the amount of loop within that magnetic field. And that's a constant quantity, or it's a constantly changing quantity. The amount of x that we're introducing to this field over time, that is a constant quantity. So we have the kind of this constant change in area over time. So if I'm coming back down over here to my initial, what I wrote, I'll write a little bit smaller, we have this magnetic field that's staying constant. And let me use one color for constants. Sure, let's call this dark blue a constant. So I have a constant magnetic field. My amount of magnetic field isn't changing. My area is changing. Time is kind of a thing that's just happening. Equals, because our area is changing, our current is changing, because this EMF is changing. And then our resistance is just going to be constant. So I can break this area down even further, because I said before this area was x times y. So I can say, oh, well, I have b x, the amount of x was changing, but the height in there was not changing, so I have this y is constant. What it looks like. So the current is maybe changing. So then if we look at this, we said, oh, well, our change in x over time is just going to be our velocity. We said that the amount of horizontal distance that we're changing over time, that's our velocity. So let's write that. V times Vy equals I times R. So instead of x over t, we're saying, oh, our change in x over our change in time is just our velocity. We can write position over time as our velocity. So then if we're looking at this, oh, it looks like, if we're thinking about what's constant, this magnetic field is constant, this velocity we said was constant, this y is constant, this r is constant, which means that our I is constant. So that's a huge idea. This over here, this is big. Let me erase this. So we said that when our flux is changing, we induce this current. So when our flux changes, we induce, so over time, we get an EMF, or we get a current. So at every point in this instance, when our flux is changing, it looks like it's kind of changing with this constant amount. So we see every time we have a change in flux, we're going to have the same value of current. That's what this whole explanation was about. We're going to have the same value of current every time we have a change in flux. So for part one, or time one, it looks like we go from, we have a little bit of magnetic field, and then an instant later, kind of thinking about this as just like a brief little instant, either before or after. So right before it, we had a little bit of less magnetic field. And right after it, we have a little bit more magnetic field. So during this point, our area within the magnetic field is changing, so we have a flux there, which means we have a current. In this case, we also have our magnetic field. A little bit before was less, a little bit after is more. So we also have a flux here. So that's good to go. We also have a flux, which means we have the same amount of current. And then in this case, we go from, oh, well, we have the same amount, we're fully in this magnetic field, so we're only able to encapsulate the amount of our maximum area in here. So this one will not have a change in magnetic field within that area. It will not have a flux. So this one has no flux, which means it has no current. So we know that T3 has no current. So now the final thing that we want to look at is the direction, if there is one present. So we can do that pretty straightforwardly. That's probably our easiest part of what we have going on here. Oh, just getting in. Oh, that was nice. I knew. Okay. So in this case, I have some amount of this magnetic field that's into the page. If we look at a little instant beforehand, or even more extreme, way beforehand, we had no magnetic field into the page. In here, the magnetic field is going to it doesn't like change. It wants to go back to what it used to be. So it doesn't like that change. It wants to go back to how it was. So it's going to try to induce a magnetic field in here. That is, it's supposed to be smaller. It's going to try to induce a magnetic field that is into the page, because it wants to go back to the spot where it said, hey, before I had no magnetic field, I was happy, and now I want to go back to this spot. Alright, well, let me grab them all. But it wants to go back to how it was before, where there was no magnetic field. So it's going to induce a current that is, or a magnetic field that is into the page. In order to do that, we're going to look at our second right-hand rule and say, okay, if we want a current that is out of the page, so this dot represents this out of the page. I think I was saying the wrong thing. Sorry about that. So it's going to induce a magnetic field that needs to be out of the page to cancel out the one that's into the page. So to get us out of the page, we need a current that is going in the counterclockwise direction. And then same thing over here. Again, it's still saying, oh, well, I'm not fully in. I'm used to having no magnetic field over here. And once I move inwards, I'm still going to need to induce a magnetic field that is out of the page to get me back to how I was before, because I don't like this new change. So it is going to try to induce a magnetic field that is out of the page. And in order to do that, we still need a clockwise current. And what we argued before was that it is the same value. So this has some current. This has some current that is counterclockwise. And they're going to have the same amount of current based on what we argued at the very beginning. So I didn't really write a paragraph, but I kind of argued the reasoning. So it wasn't really clear and coherent. So let me just type something up really quick. I'm just getting my keyboard back. Alright, so if we're going to type something up, I'm going to come over here. This is kind of our key, so it's a little bit of cheating, but you know, that's okay. So this we're going to say, at time t1 and t2, let me see what we're really trying to answer again. Compare the magnitude, yeah, the magnitude of the current loop of wire is the same. And they are in the same direction. So that's kind of our thesis, what we're arguing. So we can say something about, for the magnitude, the loop is moving at a constant velocity, which means our area is changing at a constant rate. So that's kind of our relevant observation. We notice that the loop is moving at a constant velocity, which then tells us that our area is changing at a constant rate. Magnetic flux, not magnetic flu, that would be bad. Magnetic flux is the magnetic field within an area of wire. When the magnetic flux changes, a current is induced. So that is just facts, that's physics knowledge that we know. Now we can kind of tie that together and tie that back into our thesis. So when the magnetic flux changes, a current is induced. The rate of, or I'll say maybe, because the current or the coil of wire is moving at a constant velocity, the rate of change of area is constant. Because the rate of change of area is constant, the rate of change of flux is constant. Because the rate change of flux is constant, the EMF is constant. Because the EMF and resistance in the wire is constant, the amount of current in the loop is constant. It's kind of a lot of words, but it's us just arguing from a logical sense about what we're talking about. And then we're going to talk about the direction. So that's kind of, I argued it already, but so the induced current will try to counteract the new magnetic field the loop is experiencing, which means the current will be counterclockwise to induce a current that will produce a magnetic field that is out of the page, counter to what we are adding to the loop of wire. That's not a great explanation, but let's see, what did they say? Identifying it as counterclockwise and explain that the direction of the current generates a magnetic field that opposes the change in flux. Great, okay. So we said something that was close to that. And then finally, at T3, there is no change in flux because the full area of the wire is already within the constant magnetic field. We have no change in area and no change in magnetic field, so there is no change in flux, so no change in, or so no EMF, so no current induced. Alright, so that is kind of a very lengthy answer to this first one. I'm going to stop the video here and then start a new one.